Hello friends, in this session we will be discussing about digital to analog converters. Digital to analog conversion involves translation of digital information into equivalent analog information. There are two types of DACs, weighted resistor DAC. In this type of digital to analog converter, there is one input resistor for each digital bit. Beginning with the LSB, each falling resistor value is one-half the size of the previous resistor. The circuit diagram of 3-bit digital to analog converter is given here. We are having 3 bits, 2 to the power 0, 2 raised to power 1 and 2 raised to power 2. This is LSB and this is MSB here. We are having a resistor R0 for LSB. For second LSB, it is R0 by 2. For the third LSB, it is R0 by 4. The LSB has a weight of 1 by 2 raised to power n minus 1, where n is the number of input bits. The change in output voltage due to change in LSB is equal to V by 2 raised to power n minus 1, where V is the digital input voltage level which we will apply at the input here, here and here. The output voltage VA can be found for any digital input signal by using the following modified form of Millman theorem. VA is equal to V0 2 raised to power 0 plus V1 2 raised to power 1 plus V2 2 raised to power 2 plus V3 2 raised to power 3 plus Vn minus 1 2 raised to power n minus 1 divided by 2 raised to power n minus 1, where V0, V1, V2, V3 up to Vn minus 1 are the digital input voltage levels 0 or V, and n is the number of input bits. V0, V1, V2 we apply here, and they all are of the same level. For low it is 0, for high it is V volt. For example, if a 3-bit digital input 0, 1, 1 is to be converted to the analog voltage and V is equal to 10 volt, then the output will be 10 into 2 raised to power 0 plus 10 into 2 raised to power 1 divided by 2 raised to power 3 minus 1. Since we are having only 3 bits, then it comes out to be 10 plus 20. The LSB is having a share of 10, and the second LSB is having a share of double the LSB divided by 7. It comes out to be 4.285 volt. The weighted resistor DAC is having two drawbacks. Each resistor in the network has a different value. Since these dividers are usually constructed by using precision resistors, the added expenses becomes unattractive. Moreover, sometimes it becomes very difficult to find the resistors of exact value. The second, the resistor used for MSB is required to handle a much greater current than that used for the LSB resistor. For example, in a 10-bit system, the current through the MSB resistor is approximately 500 times as large as the current through the LSB resistor, because the value of the successive resistor is half than that of the LSB. Means if LSB is of R0, the second LSB will be of R0 by 2, the third LSB will be of R0 by 4, and so on. The second DAC is R-2R ladder. It is constructed of resistors that have only two values R and 2R, thus overcomes the objections to the resistive divider. The circuit diagram of R-2R DAC is given by, here we are having MSB. Earlier in this side we were having LSB. Now we are having MSB here. Please keep in mind. Then the second MSB, the third MSB and the LSB. The resistors here are R and 2R only, and this is terminated by 2R resistor. The left end of the ladder is terminated in a resistance of 2R. The circuit is having a unique property that the total resistance looking from any node back towards the terminating resistor or out towards the digital input is 2R. Means if we are standing at A, B, C or D and look towards the terminating resistance, this one, we will find the resistance as 2R. Similarly, if we look towards the input 2 raised to power 0, 2 raised to power 1, 2 raised to power 2 and 2 raised to power 3, we will find the resistance 2R. Beginning at node A, the total resistance looking into the terminating resistor is 2R. If we are standing here and look towards the terminating resistors, terminating end, we are having the resistance 2R. And if we are looking towards the input, the resistance is again 2R. For node B, the value of resistance at A can be determined using the Thevenin's theorem. If we apply the Thevenin theorem at this point A, and if we see from this point, we will find that these two resistances, they are in parallel, and the equivalent resistance will be 2R into 2R divided by 2R plus 2R. It comes out to be R, and the circuit will become as shown here. It is the resistance which can be represented from A is R, and the total resistance looking into the branch towards the terminating resistance is 2R, as is the total resistance looking out towards the 2 raised to power 1 input. The same is true if one is standing at point C as shown here, or at node D as shown in this particular diagram. Now assume that the digital input signal applied is 1 0 0 0. That is, we just want to convert this signal into the analog signal. With this input signal, the binary ladder can be drawn as shown. Here we have applied the voltage V at the MSB only, and all other points, they are grounded. As we have discussed earlier, the total resistance standing from this point and looking towards this end is 2R. So the total equivalent circuit will become like this, and the output voltage will be VA is equal to V into 2R divided by 2R plus 2R. It comes out to be plus V by 2. In other words, due to the MSB, the output will be V by 2. When the input is applied to the second MSB only, these 2 points, this is grounded, and MSB is grounded. We are having the input at this point only. Since there is no voltage source to the left of point C, it can be represented by 2R only. We have represented it 2R. The circuit comes out to be this one, and apply Thevenin theorem by cutting the circuit on the jagged line we have at this point. If we apply the Thevenin theorem, we have the voltage here at this point will be V by 2, and the total resistance comes out to be R. This is the circuit which we have obtained. Now when this circuit is solved, the output voltage will come out to be V by 2 into 2R upon 4R comes out to be V by 4. It means the output voltage due to the second MSV will be V by 4, which is half of the voltage which we have obtained due to the MSV. The third MSV will provide an output voltage of plus V by 8. The fourth MSV will provide an output voltage of V by 16, and so on. It means each successive MSV will provide the voltage which is half of the previous one. The output voltage for the binary ladder or R-2R DAC will be bit position MSV V by 2, second MSV V by 4, third MSV V by 8, seventh MSV V by 128, and the nth MSV it will provide V by 2 raised to power n. This is the complete circuit diagram of the digital to analog converter. Here we may have either of the two DACs which we have discussed earlier. We are having level amplifier, we are having certain flip-flops and gating circuitry. Now we will discuss about these points. Level amplifier is there to ensure that the digital signal presented to the network all are of the same level and are constant, because we have applied a precision voltage source over here. The level amplifier each have two inputs. One is from the precision voltage source and the other is from the flip-flop. The amplifier works in such a way that when the input from the flip-flop is high, the output of the amplifier is at plus 10 volt. The input from the flip-flop is low, the output is at 0 volt. The 4 flip-flops from the resistor necessary for storing the digital information. Each flip-flop is a simple RS latch and requires a positive level at the R or S input to reset or set it. With this particular gating scheme, the flip-flop need not to be reset or set each time new information is entered. When the read-in line goes high, only then data is read by the flip-flops. This lecture has been prepared from the book Digital Principles and Applications by Leach, Malvino and Saha, 7th edition of Tata McGraw-Hill, New Delhi, 2011. Thank you.